so in chapter 9, we finally get to talk about stoichiometry, which we actually did a little bit before, earlier in the year. It's really converting between grams and moles and particles, with the mole in between. Now we're just going to kind of take it a step further, and we're going to look at how to convert between grams of two substances, or moles of two substances. So our goals for this are to define stoichiometry. We're going to talk about the importance of the mole ratio, and we're going to write a mole ratio relating to substances. So it's going to be kind of a short lesson just to get our dip our feet in the pool of stoichiometry here. But there's a couple of different types of stoichiometry. Technically, there's composition stoichiometry. That's dealing with the mass relationships. So if we said something is 75% one substance and 25% another substance, we're telling you what it's made of, what its composition is. That'd be composition stoichiometry. On the other hand, when we're dealing with chemical reactions, like we've been looking at last chapter, that's what we call reaction stoichiometry. And that involves the relationships between the masses of the reactants and products. So just for example, you think of cooking or baking, you need to know how much, for instance, if you're baking a cake, you need to know how many eggs you need, how much flour you need, how much sugar you need, and that all is going to determine how many cakes that you can bake. Even something like manufacturing, if you're building a bike and you have 20 tires, you have 50 handlebars, you're definitely not, even though you have 50 handlebars, you're not going to be able to make 50 bikes because you only have 20 tires. So that kind of thing is what we're looking at. Those are sort of more practical hands-on examples. In chemistry, we're looking more like, if I have this much hydrogen and this much oxygen, how much water could I produce? Or vice versa. So there's actually 4 types of problems we're going to look at first with stoichiometry. And it actually makes a little bit more sense if we sort of look at the big picture. So basically, I could figure out how much mass of one substance I could make if I started with a mass of another substance. But in my formula, if there's a 1-to-2 ratio, that doesn't tell me that there's a 1-to-2 ratio of grams. Remember, those are telling us moles. So those are mole ratios. We have to go into moles first, and then out of moles if we want to go from grams to grams. So what this is telling me is I can think of it like a train station. You've got 4 stops on that train going from grams to grams. I could start at moles and end at moles. So I could, for instance, have moles of substance A and figure out how many moles of substance B I have. I could also start at grams of substance A and determine how many moles of substance B I have. Or I could start at moles of substance A and figure out how many grams of substance B I have. Or I could start at grams of substance A and go all the way through this and figure out how many grams of substance B I have. So it's basically like these 4 problem types is where do I start and where do I end. So I could find moles given moles. I could find grams given moles. I could find moles given grams. Or I could find grams given grams. So let's look at an example problem here with 2 moles of aluminum oxide give me 4 moles of pure aluminum with 3 moles of oxygen. So a mole ratio is what can get us between moles of one substance to moles of another substance. So if I have 2 moles of aluminum oxide, that's going to produce 4 moles of aluminum. So my ratio I could write is 2 to 4, or I could write it as 4 moles of aluminum to 2 moles of aluminum oxide, depending on how I want to use it. I also see that there's 2 moles of aluminum oxide for 3 moles of oxygen. Again, that can be flipped. I could say 3 moles of oxygen per 2 moles of aluminum oxide. And finally, I see that there's 4 moles based on the coefficient of aluminum to 3 moles of oxygen, or I could flip it and say 3 moles of oxygen for every 4 moles of aluminum. So that's what I mean when I say mole ratio. I'm going to mention the mole ratio a lot. When I say mole ratio, think of it as the coefficients in the balanced chemical equation. So one last note here, and then we're done with this little preview section 1. Realize that when I do use the mole ratio, I always want the unknown substance on top. So if I'm trying to find moles of one substance, that's going to go on top because I want the moles of my known substance to cross out, to cancel out. So the moles of the known substance will cancel out. We'll look at some example problems tomorrow that use this, but for now, just want to introduce you to the mole ratio.